Good evening, and welcome to this webinar presented by the IET's Cambridge Network. We represent members from in the Cambridgeshire area, but we're also pleased to welcome people from across the UK and tonight from around the world. My name is Phil Zengast. I'm the chair of the local network, and I will be your host this evening. Now, before we start, I will mention some housekeeping rules for tonight. We will leave questions to the end of the presentation. So if you think of a question, please remember to use the Q&A button, please. That's the Q&A button, not the chat button. And you can find that down at the bottom of the Zoom screen if you wiggle your mouse. So we'll try and answer, or our speaker will try and answer all your questions tonight. But if there are any left over, we'll capture those and they'll be answered offline, and we'll publish those later. And we will be recording the webinar tonight, so that will also be available later. And finally, I'd just like to mention our next event, which will be on the subject of renewable energy. And that will be next week on the 26th of November. So I'll now hand over to my colleague, Annie Liu, who will present our speaker tonight.
Thank you, Phil. Good evening, everybody. It's my pleasure to introduce Andrew Monk this evening. Andrew is one of the co-founder and director for ioLight magnificent mobile microscopes since 2014. Andrew have held CEO posts in technology startups, closely follow optical technology and growing diverse businesses that create innovative products and services in the technology sector. ioLight has invented and patented a portable microscope, the technology of which we are going to hear about this evening. I will now hand over to Andrew Monk.
Thank you, Annie. I'll just find my slides. Good, hopefully everybody can see that. Good evening, everybody, and thank you very much for turning up to this presentation. It's great to see so many people here. Thank you for your time. So I'm going to talk about the microscope and how we reinvented the microscope and came up with this little microscope and why. So hopefully that will be interesting. So microscopes have been around a very long time, actually. Let me just minimize this. So lenses have been around since the 13th century for spectacles and hand magnifiers. And this diagram here shows how a simple lens works just to make objects bigger. People have seen this through water drops for thousands of years. And in the 13th century, lens makers were highly valued right the way across Europe. Particular favourite of ours, a huge inspiration to ioLight, is Antonie van Leeuwenhoek, who worked in Delft in the Netherlands, what is now the Netherlands, in the 17th century. Van Leeuwenhoek used one of those single lens microscopes, and this is an image of it here. You can see there's just a single ball lens, and the sample is mounted on this pin, and the three screws here, here, and here allow you to move this in the X, Y, and Z directions, and you look from the other side to the sample very close. Van Leeuwenhoek developed a fantastic skill at making these lenses, which he did by drawing fibers, heating up rods and drawing fibers and then fusing the ends of them. And this technique wasn't replicated until 1957. And Van Leeuwenhoek discovered all sorts of things that we now take for granted: protists, single-celled animals, spermatozoa, the muscle fibers, all sorts of things. The structure of blood, and he was a fantastic illustrator. He do have a look at his drawings. He made some really, really beautiful drawings. But the real step forward was happening at about the same time. There's a lot of discussion as to who invented the compound microscope, but the idea of a compound microscope is to increase the magnification. So here is the object. The labeling here is a bit confusing, so apologies for that. Here is the object we're looking at, the little arrow, and then we form, using this objective lens, we form a virtual image that's sometimes called image one inside the microscope tube. And then we look at that image using the ocular or eyepiece lens, and that magnifies the image again. And so you get a big image that appears to be in this at a long distance the other side of the lens, and greatly magnified and inverted. So that's a compound microscope. And the earliest claim to that was by Zacharias Janssen, although some people suspect this claim because the claim is that he invented it in Middlesbrough in 1590, and he would have been 5 when he did that. And we've got some fairly smart toddlers around, but maybe it was his father. The next instance was Cornelius Drebbel in London in 1621, who needed to raise some money to, Wikipedia says, to pay for the loose behaviour of his wife. It doesn't say what that actually means, but I was fascinated by that phrase. And various other people took the design onwards, notably, of course, Galileo, who is famous. What he did was he turned his telescope round and looked through the wrong end of the telescope, and found that that was quite good, but having a microscope that was 2 meters long was probably too big, and I agree with that. So this design has some fantastic strengths, some really good strengths, and it's used all over the world, and we all see them every day in labs and schools and everywhere. The strengths, one of the strengths is down to the what's called the tube length. That's the distance between the objective and the image one, the virtual image. And this is standardized in the vast majority of modern microscopes to be 160 millimeters. And if you standardize it, then what you can do is you can change the objective lens, and you can change the eyepiece lens or replace it with a camera. And as long as you use this standardized length, you know where the image is. So you can focus, you can choose your ocular to focus on that image, and you don't care what the objective is. Similarly, you can swivel your objective turret and select any objective, or even replace them with different ones from another manufacturer. And as long as you're still working on 160 millimeter tube length, you're okay. So that's one of the big flexibilities of the modern compound microscope. Another benefit is that it has very large magnification, because the magnification is the product of the objective magnification and the eyepiece magnification. So typically you might use a ×40 objective and a ×10 eyepiece to give you ×400 magnification. You have to watch this, because quite often customers talk about, oh, I'm using ×40 magnification. They mean ×400, because they've forgotten that they have to include the eyepiece as well. And that means that you can change lenses, you can have very expensive high quality lenses, and you can use cheap and cheerful lenses if you just want to try something out. So that's a very, very good feature of compound microscopes. Unfortunately, they also have some weaknesses. They're at least 250 millimeters tall. If the tube length is 160, then you have to add a stage and illuminator below that, and the adjustment and the illuminator, and the stand. And because it's tall and thin, it's inherently unstable. It's the sort of, you're balancing a pencil on its point. And because of that, you have to make a big chunk of heavy metal, quite often cast iron, on the bottom to make sure it doesn't fall over. And you also have to be able to adjust the stand, as this scientist is doing, while you're looking through the microscope. So that has to be, you have to be a bit careful that you don't, anybody who's used a compound microscope will know that the risk is that you put the objective lens through the slide and risk breaking the slide. And so that's a problem. And there's no image capture as standard. You can have a trinocular microscope like this one, where you can add a camera, typically a DSLR on top, and capture the images. but that quite often doubles the cost of the microscope, very expensive indeed. And as this scientist should know, you need mains power, and she's forgotten to plug hers in, which is why I love this photograph. So you need mains power. So all of this means that it's definitely not portable. It's very difficult to take a compound microscope anywhere. People have done it, and this is my favorite photograph. This is my friend Munib Kanyari from the University of Bristol, and they went out to Kazakhstan a couple of years ago, can't remember, 2015 I think it was, when there was a Saiga antelope disaster. The lovely Saiga antelopes were dying. They were just finding them in heaps right the way across the steppe, and nobody knew why. And a lot of vets, including Munib, went out there to try and see what was going on. And they took with them their standard lab microscope, compound microscope here. And they also took their ioLight microscope just for fun to find out whether it would work or not. Well, they drove for 2,000 kilometers across the steppe in a Toyota truck. And when they got this out of its box, it had rattled to pieces and it didn't work. So this photograph is great. This microscope is not working. This one is, and is producing some nice pictures on Munib's phone, which he's able to store. And if there was mobile coverage, which there probably wasn't there, he could share those immediately. So this is the portable microscope. So lab microscopes are definitely not portable. They are tricky as hand luggage. You always get asked difficult questions if you carry one onto a plane. They're fragile. They're not really suitable for field use. And that's a real and increasing problem nowadays with climate change. A lot of scientists are working in the field, looking at climate change, looking for the impact on the smallest subjects, on protozoa and algae in the most remote places. So at Everest Base Camp, for example, National Geographic, we're looking at that. Our customers have used them in Antarctica. But it's not just climate change. Field servicing is a big issue. If you need a microscope for asbestos servicing, for example. Also exhibitions, if you've ever displayed something microscopic at an exhibition, you'll know it's an absolute nightmare with the queues of people to look down the microscope, and conjunctivitis is very infectious, so it's actually not a very good thing to do. And the big goal for us is point of care diagnostics, where you can actually go out into remote places and diagnose disease in animals or humans or crops or anything. So having a portable microscope is a kind of useful thing. And the first portable microscopes since Van Leeuwenhoek appeared in about 1930. They were invented in America by John McArthur. And some of you will have seen these things. They're absolutely great. We love them. So this is, there's nothing here to show you the size, but it kind of fits into your hand. It's a bit clunky. It's got a rack of interchangeable lenses that slide in and out here. So you've got proper optical, very good optical quality, but they're kind of awkward to use because you have to peer down this lens at the same time. You have to get the sunlight to shine in through the illuminator here, and you have to move the slide on this stage here under the clip and focus the microscope here at the same time. So you're kind of looking down and it's kind of really hard. And quite often people use these on tripods to try and get a bit more stability and make them a bit easier. The standard ones also had no camera, although people did try and adapt it to add a camera. And these were hugely successful from 1930 through to the 60s, and actually you can still buy them today. They are poor copies of the original McArthur one, and collectors love these things. And there's some very good antique microscope websites with pictures of these on. But this is a role model for us. This is what we want to do. We want to have a microscope that is fairly inexpensive and can be used in the field easily and gives nice quality images. With the advent of digital microscopy in the 1980s, that was very soon miniaturized, and many of you will have seen these. You can buy these on Amazon for about 15 or 20 pounds. And they just use mobile phone components, and they're great for low magnification applications, particularly if you've got kids. If you've got kids who are interested in science, or you'd like them to be interested in science, get one of these from Amazon. They're great. And you can look at bugs, and you see them on your mobile phone, and they're widely used in electronics assembly, on production lines, science teaching and outreach, but they're not powerful enough. They haven't got high enough resolution to view cells, because you can't hold them still enough. You need a bottom illuminator, the other side of the slide, and just the resolution of the lens and the optical system is not high enough. The original was done by Dino-Lite, and they're still a very good supplier of a huge range of these things, and they're widely available. But if you're going to take it into the wild, the actual microscope itself is very portable. In fact, you can get battery operated Wi-Fi versions of this, which are very portable, except for the fact that you need a laptop to view them on. You need a stage to hold the sample on. You need a clamp, you need a retort clamp to hold this still, otherwise you're not going to get anything like decent resolution. And an illuminator, and if it's not wireless, you need a cable. So all of that is a pretty decent rucksack full, and if you're climbing Mount Everest, you really don't want to be taking all that stuff. So I bumped into my old buddy, Dr. Richard Williams, back in 2012. We'd both been working for a company in France, and were both looking for the next job. And Richard was telling me that he'd made a microscope in his garage for a client because he didn't understand why he couldn't buy a decent quality microscope just for use on projects. Microscopes were either very expensive, they had no camera on them, or they were just a bit rubbish. And he sent this image to me. I was on a bus in Brixton, actually, and I jumped up and I said, "This is fantastic. Richard has just sent me an image of cheek cells, and these cells are about 10 microns across. The nuclei are much smaller than that. That's quite a good image for a portable microscope." And so we got very excited and inevitably met up in a pub, the Crown Inn in Highfield in Southampton, which is a very nice pub. And we drew up a spec for what we might be able to do. And what we wanted to do is to build a pocket microscope that was based on the proof of concept that Richard had built in his garage. The aim was to produce a performance that was 90% of a lab instrument. One of the things that we're excited about with technology development is if you try and do what the mobile phone does, or what the laptop did, or the personal computer did, and develop something that's not better than the predecessors, stop trying to get better and better and better with innovation. Do something that's 90% as good, and you'll find that there's all sorts of savings that you can make to make ease of use better, to make it more flexible, to make it more usable and more user-friendly. And of course, the performance comes as the product develops anyway. So we definitely wanted an XY stage. You can't get high resolution without an XY stage, as we saw from the Dino-Lite. You need, for biological samples, which is the main market, you need top and bottom illumination. And it needs to integrate, we wanted to integrate with the mobile phone. First, we wanted to use a mobile phone as the camera, and there are lots of people that do that. You can buy clip-on lenses that go with mobile phones. But because the mobile phone is built as a telescope, it's the wrong way round, and before you even get started, you have to start undoing the damage that's been done by that way. Richard used to say that yes, you can do that, and he'd get a scalpel out of his pocket and start cutting the lens out of people's iPhones, and they got very excited very quickly. We wanted it to be wireless because when you're in a remote place, the last thing you want to do is to carry around a bag of wires. And we understood from the beginning the potential of connecting to the internet, sharing images instantly for a second opinion, and perhaps even using artificial intelligence to identify and diagnose the images. So we started to wonder why there were not so many portable microscopes around. we always worry when we're innovating. You always worry if nobody's done it before. Your first question should always be, why not? And the answer is a commercial one. The market, the microscope market, optical microscope market, is dominated by 4 big companies: Olympus, Nikon, Zeiss, and Leica. And these companies specialize in producing better and better and better microscopes. They produce beautiful microscopes, really nice products, and some of them are quite expensive. If they tried to start innovating and make them smaller and 90% as good, less good, of course, their customers wouldn't be happy because their customers are asking for better and better products, and they'd make less margin, because if you're selling something at a lower price because it's smaller, then you're making less margin. So actually, it might seem like a good idea, but the minute you start to present it to the board, it's obvious that these companies find it very difficult to innovate. And here I'd like to plug a wonderful book called The Innovator's Dilemma by Clayton Christensen, who sadly died a couple of years ago, but he was the professor of business administration at Harvard. And it's a great book because it explains how I've always thought innovation works, and it blows away some of the myths about having to be better, faster than everybody else. No, you need to be more user-friendly. You need to innovate and do cool new things. So what are the design challenges of developing a pocket microscope? Well, there were quite a few, and at the meeting in the Crown, we got quite intimidated quite quickly. Firstly, microscopes use large, expensive optics, these big lenses that you're supposed to use. And even if you just put the lenses in your pocket, you know you've got something in your pocket. So it's going to be quite hard to use those big optics to make a new microscope. And particularly as the existing optics all work on this tube length of 160 millimeters, that means that the microscope is going to be at least 160 millimeters tall and more when you put the stage and illuminator underneath it and the eyepiece on top. Not only that, but the stage has to hold the slide very, very still. And we're looking at micron resolution. So the tolerance in this engineering of this joint here is 1 micron. And that's quite hard to do. So you've got the optics perpendicular to the stage, and that ain't going to fit in your pocket because the thing is cube shaped. And unless you've got very odd pockets, that's not going to fit in into your pocket. And then we came across the technical problem is that we wanted wireless video over Wi-Fi, and you can forget about Bluetooth, the bandwidth's not high enough. So using wireless Wi-Fi, we wanted 0 lag, because if you have lag in focusing a microscope and moving the slide around, you're going to throw it out of the window very, very quickly. It's just maddening if you've got that lag in there. And you might say that video over Wi-Fi is a well-known technology. Some of you might even be using it to watch this this talk, because Chromecast and Apple TV and all these various other wireless techniques are very well known. But what they do is they build in a 2-second buffer. So what you're watching on the video is 2-second delay from what's being broadcast. Now, if you're watching a film, that's not a problem. If you're watching a news program, you're getting your news, you're hearing about the American election 2 seconds later than everybody else, but that's not such a big deal. But if you're focusing a microscope, 2 seconds is going to drive you absolutely bananas. It will just be totally impractical. And on top of all of this, Richard and I decided that we didn't really know what the market was. So we didn't want to put millions of pounds into this, and we'd start on a very low budget. So we started by funding it ourselves, with the third member of the team, John Foster. And so the budget we were working with was tiny. So this was quite a challenging design brief for us. So to address the first problem is the large expensive optics. We knew that mobile phone optics are great. And this is a picture of a Samsung camera, a Samsung Galaxy camera. These mobile phone optics, the lens quality is absolutely brilliant. People get sneery about plastic lenses, but the quality of these modern phone lenses is absolutely brilliant, and we love them. The problem is that they're not designed for microscopes. We could design a new lens, but that's going to cost hundreds of thousands of pounds to set up a production line to custom engineer a new lens. So we had to use the existing mobile phone lens, and that needed some very careful optical design to make sure that we could correct for most of the aberrations in this lens when we're using it as a microscope lens. In here is a 5 megapixel sensor. Typically it's an Omnivision sensor, and that's a great match for the optics. People say, why don't you use a 40 megapixel sensor or a modern sensor? Well, it turns out that the image that we're forming with this lens, actually a higher resolution sensor doesn't help us, because the limit on the optics is the lens, not the sensor. We may go to a higher res sensor in the future, but for now, the 5 megapixel sensor is not limiting the performance. And the really cool thing we find in here is the little voice coil motor. I don't know if you know, but the mobile phone, the lens on the phone is focused by a little voice coil, and it's micro positioned. It moves backwards and forwards by about 1/4 of a millimeter. And it's like a loudspeaker coil that drives the focus in and out. And that meant we could do the last bit of fine focus electronically without our hands on the microscope, which is great, because the last thing you want if you're trying to focus a little microscope is your big fat hands on the thing. The coarse focus is much easier to do by hand, but you need that fine focus on the end. So how do you fit it in the pocket? That was the big problem. Well, this is our patent. We used a hinge, and this is not obvious because hinged microscopes through the ages have been awful. If you look at the McArthur or any other successful microscope, they stay away from hinges as much as possible. But actually the engineering in this product, the difficult part was designing this hinge, and Richard is a fantastic engineer. He had to give our product engineering team a lecture on tolerancing, because engineers know all about tolerancing and how to add up tolerances, but you can't do that here because the tolerancing is too tight. You have to actually build it and make sure that you can allow for the tolerance, and you can get that tolerance down to within 1 micron in a hinge that's actually doing quite a lot of work. We also forget about the tube length. We forget about that because it's not a compound microscope, so we don't have to have that 160 millimeter of height. And we've got, as well as the stage, which is essential, we've got an illuminator here around the base of the microscope, and a second one in the head around the objective lens, and the camera sensor is up here. And the product as a whole is 32 millimeters thick and weighs a pound in old money. So it really is very small and portable and easy to carry around. So the wireless video was, I hope you can all see this video. The wireless video was interesting. That was a real problem, and we thought that was going to be a showstopper. We talked to a lot of wireless companies, and they said, oh, it's going to cost you a lot of money, that. And then we suddenly came across the Raspberry Pi, which is a fantastic Cambridge product, which many of you will know about. The Pi is absolutely brilliant for us because it is great at handling graphics. Its video processor is the Broadcom processor, and it's really good at doing what we want to. So that was all built in. We had to take off the lag, and that did give us some problems. But it meant that we could develop the first product with very little software. It also has a built-in Wi-Fi adapter and a slot for a USB Wi-Fi connection. It's easy to write the code, and there's loads of I/O to control the illuminators and the stage manipulators and so on. And what we get out of that, I hope you can see this video running. It's about to finish and we'll start it again. This is a Daphnia, and you can see there's a little kick at the beginning, but here you can see the animals. It's a water flea. This is its heart beating. And I just love this video because we just pulled this out of the pond at the Royal Agricultural University at Cirencester, and we got this great video. It is, I think it's one of the best entry-level video microscopes around. It really is a very good product, and you get the video for free. You don't have to pay for an extra camera. So there we are. That's a very quick guide to our little microscope. It's highly portable. we can get 1 micron resolution on that, which is enough to see cells. That's the big cutoff for biologists. If you can see a cell on it, then it's a proper microscope. If you can't, then it's a toy. We have very low lag video. You don't notice the lag at all. Obviously, there is a little bit of lag, but you don't notice the lag at all when you're using it. It's very easy to use. And it's robust. One of my favorite stories is dropping it from the repacking area in Gatwick Airport. Remember when we used to go on aeroplanes? I dropped it onto the floor when I was repacking my bag, and the security guys were very worried to see me measuring how high the table was. It was 1 meter onto a concrete floor, and no ill effects at all. So it is really tough. It's been to Antarctica twice. National Geographic have taken it up to base camp on Mount Everest, and that's a great story, which I can tell you another day. It's been to the Amazon rainforest. It's been it's been to every single continent in the world. We've sold 350 of these. It's been to a lot of places. And if you want to look, the full story is there on our website. So that's the end of my slides. Thank you for your patience of going through those. I was wondering whether you'd like a little demonstration so that we can see. I'm just going to stop sharing my screen. Good. So I'm going to. I've got a little microscope here, and my plan is to just give you a little demo on this microscope, just on my table here. So I'm going to do that. I'm going to move the camera down. And the reason why I wanted to do this is just to give you a feeling for how simple it is to use. So this pouch is really very small. My hands are slightly bigger than normal because I'm a bass player. So bass players have big hands. But it's a fairly standard small jacket pocket size thing. And it comes out of the Velcro bag. And here it is, and here's the hinge I was telling you about. That's the clever bit, and the microscope just unfolds like this, and there's a nice click as it hits the detent, and we focus it like that using the head. You can use the purple buttons are brakes, you can use those, but actually I think it's easier without them. So there's the microscope, and somewhere here I've got an iPad. Here we go. So the microscope contains a wireless access point. Whoops, using that upside down, that's not going to work. So I'm just going to log on. Could you all close your eyes a minute while I put my code in? Thank you. You can open them now. So the picture comes up on the screen. I've connected this already to save some time, but it is really quick to connect. So completely wireless connection between the iPad and the microscope, so you don't have to carry lots of cable around with you. So we'll start with well, perhaps you can guess what this is. And just put the slide under the head. You won't see great detail on the screen across Zoom, but I hope you'll go with me on that one. You'll see something. There are loads of pictures on our website, and I'm happy to share any of these pictures with you afterwards. So here we go. I'm just moving this by hand, and already there you can see there's an image on there, and I'm just going to move down. Ooh, where's the other end gone? I've got it upside down. Yeah, so I'm just moving down this leg. This is the leg of a bee. It's the pollen collecting leg, and so we can focus it quite closely, and you can, I don't know if you can, no, you probably can't see, but I can see the hairs on the leg here, and you can using that voice coil, I can move it in and out, and we can see the different parts of the leg in focus at different times. And for those of you into microscopy, we can also do Z stacking, so we can take a stack of images through the depth of the product. We can also do some histopathology. So this is a slice out of a fish in this case. Of course, we need to refocus because the slide is a different height. I'm just refocusing by hand, which is a lot easier than you think it's going to be. Okay, I've done it a few times before, but there we go. And you can see, I hope, up here, there are some this is a fish, and these are the gills that you can see. And again, these slides are on our website, or I can share them with you. So those are the gills of a fish. So you can see that very easily and quickly. If you're out there in the field, you don't want to be messing around for a long time with getting a perfect image. You want to be able to get something quickly, and we can capture using these buttons here. We can capture this image, we can save it. This is a video preview. So the captured image is a full 5 megapixel resolution. So they're quite nice images, as you can see. We can also take videos, and there's fine focus. We can change the illumination. So this is the bottom illuminator, and the other button is the top illuminator. So you can view opaque samples or transparent samples. So that's all I have to say for now, although I'll be very happy to hand back to the chair and take any questions.
Thank you, Andrew. I'll now hand over to my colleague David Blake, who will take us through the Q&A. Thank you, David.
Well, thank you very much, Phil, and thank you very much indeed, Andrew, for a most illuminating, I use the word illuminating talk. We have a few questions coming in, and we also have a request for somebody to talk to you. So I will start on the questions and answers first. The first one was from Sterling Essex, who asks, can you use the voice coil lens actuator to enhance the depth of field of the image, i.e. multiple images at different focus settings?
Yeah, you can, and that's I alluded to that briefly. That's called, microscopists call that Z stacking. So you can use the you can't do it on an iPad, but you can use it if you're using a laptop. You can set up the microscope so that the highest position is the top of the sample, and the lowest position is the bottom, and it will move the voice coil will move the lens through 12 positions and take a stack of images, and you get a beautiful 3D picture. And actually, that's just been used in our first published paper. Entomology is a science where that's a real problem because bugs are quite tall. So that's a very useful and unique feature of a portable microscope.
Okay. Another question is, as the camera acts as a Wi-Fi access point, can you technically connect multiple devices to it and share the same image between them?
Theoretically, that's possible. There are some user experience issues, because if you've got a class of 30 kids all trying to control a microscope and focus it differently, that's going to end in tears. We may do that one day. A lot of people think they want that, but when they actually try and use it, they realize that actually it's much better to stick the image up on a screen, which of course you can do very easily. So yes, in theory, give me a big purchase order, we'll work out how to do it.
What's the maximum magnification available?
Oh, okay, so I'm glad somebody asked this question. Thank you very much. Magnification on digital microscopes is not quite the same as it is on optical microscopes, because magnification is the ratio of the image to the object, and there is no image here. Well, there is, but it's inside, it's on the sensor, you can't see it. So the maximum magnification depends on the screen size. I can do times 1,000, times 5,000, no problem at all. The problem is, of course, with digital imagery always is the resolution of the image. So you'll start to get pixelation, and the quality of the image will deteriorate. And so it's a matter of opinion as to where that happens. We're very, very comfortable at times 200. I think it looks great at times 400, but some of the biologists might disagree with me. And we can go up beyond that. Times 800 is okay, but you definitely don't think you can give the same quality times 1,000 images you would do with a good optical microscope.
Okay. Alex Wood has got a couple of questions which will link together. And you first of all said that the sensor resolution is not a limiting factor on performance, but also you might go to a high resolution sensor in future. Why? And what developments do you have planned?
Yeah, so that's a constant development. If we were working with a different lens and we custom engineered our own lens and we used a glass lens, the optical resolution would be better. At that point, it would be better. It would be worth switching to a higher resolution sensor in the camera. and then you get the problem of the Wi-Fi gets more difficult because you're streaming more data. You've got more pixels to stream from the camera, and then you're up against Wi-Fi issues. So the whole thing is a balance between the optics, the sensor, and the Wi-Fi. We will have to go to a higher resolution sensor because the Raspberry Pi no longer uses a 5 megapixel camera, so we will have to upgrade to another camera in due course, and we're looking forward to those challenges.
Good. Going on to one of the more normal questions, how much does one of these cost?
So we've got a wide product range, and we've got inverted models, we've got a fluorescence microscope. The base entry microscope in the UK is about £800.
Okay, that sounds reasonable. A few more. How do you change magnification for a fixed screen raster size, and what is the effective? There's no, the question comes to an end.
Yeah, so the way you do it is you just pinch and zoom on the video, and the video resolution is lower than the captured image, as I said. So eventually, by pinching and zooming, you're going to run out of magnification on the on the video. So then the thing to do is to capture an image and save that to your photo library, to Google Photos or to the photos on the iPad, and then zoom in on that image, and then you can get really quite nice detail on that.
Okay, John Grant's asking, he'd be interested to hear, possibly offline if it's too long an answer, how you minimize the latency over Wi-Fi. And also, how are you looking at DECT to 2020 for future low latency radio?
Yeah, it's not really the radio that's an issue. I mean, there are all sorts of radio protocols you can use. Wi-Fi is pretty good at you know, the bandwidth on the Wi-Fi is not really it's the timing of the buffers and shoveling things. We use a piece of technology, and this is not proprietary because it's widely known to Raspberry Pi people. We use technology called GStreamer, and GStreamer allows you to configure the latency of the buffers at both ends. So it allows you to shovel bits in and out very quickly. And it's a very good protocol and is widely used. We're hoping that some of the technology that's used in drones is going to mature over the next few years, and those chips are going to become available because they're doing exactly the same thing as we are. If you've got a drone and you're using a mobile phone, the low latency of that is a very similar problem to the one that we've got. But for now, the good old Raspberry Pi is a very good development platform for us.
Okay. Is the camera sensor a dual pixel sensor?
Dual pixel.
This is anonymous attendee, so I can't, unless they want to put another question, I can't sort of offer anything more than that.
That might be a Nyquist theorem question where you have to, when you're calculating the resolution, you think there's going to be 5 million resolution points. There actually aren't. There are 2.5 million because you need 2 pixels, according to Nyquist theorem, to detect one sensor. So,
okay. Could control of the XY axis be achievable?
Control of the XY axis. Yeah, that's a question we get asked quite a lot. So there are 2 parts to that. Firstly, on a conventional microscope, you have an XY stage that allows you to move in straight lines backwards and forwards and left and right. And this is really important if you're scanning an image. For example, you're using a hemocytometer to look at an image and actually make sure you've counted things. And we've recently launched an XY stage, which is also patented for this microscope, developing an XY. So those of you who've used microscopes will know that an XY stage is a big thing like this, much bigger than our microscope. And there's no way that you're going to be able to carry that up and down Everest. So we've managed to miniaturize that. It was actually quite a tough one, but we've now got a pocket-sized XY stage that fits in the same bag as the microscope, with the microscope. And that allows you to plot, track left and right. It's still manual though, you still have to drive it. And the original plan, the original spec was to have X and Y motors so that it was automated to allow you to scan, which would be great. And we will still do that. In fact, we actually bought the little motors. So if anyone wants to buy a couple of 100 miniature motors, we've got a bag full of them. So we will do that one day, because scanning is obviously a great benefit on a microscope like this.
Okay. Still quite a few pouring in now. Is there any data compression or scaling factors between the chip and the file image? Have you had to disable any iPad processing to achieve the best outcome?
Yeah, the iPads, we've disabled some of the iPad processing, yeah, and Apple loves to process images. So we switched that off. That's reasonably straightforward. Obviously, there's processing between the sensor and the Wi-Fi, because otherwise you couldn't get the bits out. But GStreamer is very good at doing that for us and controlling that. We use JPEG images, and some microscopists don't like JPEG because it is compressed, but actually you need it to be compressed, because sending every pixel across this link would just slow it down. And actually, in our opinion, the JPEG compression is very, very good. The only problem comes when you start to do image processing using Photoshop or ImageJ. Some of the image processing packages don't like that raster that JPEG uses. So we can save the file as a bitmap or a raw file as well. So again, it's getting into and using the image processing in the most space efficient way to do that. Okay.
Will 5G technology be of benefit in the future?
Yes, so that's a good question. It'll definitely be a benefit in sending the data back to base so that your colleagues in the lab can see what you're doing on the top of Mount Everest. And at first thought, it seems, oh, we can make the microscope 5G and we can communicate directly from the microscope. But you still have to see an image. The whole idea of using an iPad or a mobile phone, most of our customers use mobile phones, is so that you can see the image and focus it. So actually being a couple of kilometers away from the microscope doesn't help you unless you've got really long arms. Quite often we get asked what the range of the Wi-Fi is, and the answer is it's at least this big, because if you're focusing the microscope with one hand and looking at your screen with the other, that's the furthest you need to go. There are one or two exceptions to that. So for example, we make an inverted microscope that's used in incubators, just simply because it's a small space, and if you can put a microscope inside the incubator, like my fridge behind me, if you can put a microscope in there and leave the experiment in there, then you don't disturb the experimental conditions and you can monitor it remotely, which is a really big feature. And there you might need to be a little bit further away, and you need to get the signal through the wall of the fridge. So some of these more modern protocols might be useful, yeah.
Okay. How did you make the hinge so precise when others have failed? I think people obviously have experience of.
Yeah, yeah. It's you need to talk to my colleague Richard Williams about that. He's a great engineer, and I love working with him because he builds things. He doesn't sit there and theorize for too long. He gets his hands dirty and makes things, and you have to be careful, as engineers know. There are shapes that you can tolerance differently. So for example, if you have a conical bearing, eventually the bearing will bind on the surface anyway, and it will self-align. So using tricks like that is how we did it. But of course, you can't use the simple cone, because if you tighten it too much, then it doesn't rotate at all. So this was the big design problem. And the other answer to that question is lots of microscope grease. Microscope grease is brilliant, and it's used for a reason, and it's very good at just a little smear will make a bearing, a well-designed bearing, feel really nice. And one of the things that we were very keen on is getting this bearing and the hinge so that they felt, you know, nice and smooth like a microscope, and that's really important to us. So the way that we manufacture this with just the right amount of grease on the side is really important.
Okay. Just a few more, because those time's getting on, but what sort of video image compression do you use, and does magnification then lead to image artifacts?
It's an MPEG, so it's an MPEG 4, and GStreamer again is very good at sorting that out. We don't, we occasionally get pixelation if the Wi-Fi signal's not very good. If you're in a very noisy Wi-Fi environment, that can happen. But our advice then is to take it out into the jungle or up Mount Everest where there isn't any interference. What video artifacts are not really a problem. To be honest, I've never struggled with that.
Okay.
The biggest problem is dirt on the slides, but that's true of all microscopes.
Another marketing issue, where are they manufactured and what is your usual sales method?
They're manufactured in Southampton. So this
Brilliant.
is definitely made in Britain, this product is, and also it's not just made in Southampton, but all the components, so the molds are made in Bishop Stortford, the extrusions are made in Gloucestershire. It's a very high UK content, this product. And the reason for that is we need to keep our hands on the early versions of this. We need to keep our hands on this. As you can tell, there's a lot of potential quality control issues here. And we need to be absolutely sure we've got the quality nailed. We will start to subcontract manufacture after a while, but for the moment, the final assembly and test is all done by us. So yeah. And what was the second part of that? Sorry, David.
What's your usual sales method? Presumably.
We're working this out at the moment, and anyone who's got any ideas, I'd really appreciate thoughts on it. Because the market that we're accessing, this market of adventurers and people who go to far off places, is a new market. And all the marketing books tell you should never launch a product that targets a new market. They're right. So we use multiple different methods. We sell quite a bit on our website, just live. We sell through Amazon, which is horrible, but it's good advertising. And we have a distributor network around the world. So most of our products, more than 50% of our sales are in the USA. More than 65% of our sales are export. So we sell through distributors in China, EU, right the way across Asia, South America. We've got a major distributor in the US and a couple of minor ones. So yeah, the sales chain is building. But anybody who's got ideas of sales channels, I'd love to hear them. What we do know is it doesn't sell very well through traditional microscope sellers because there's not enough space in the catalogue alongside traditional Leica and Olympus microscopes.
Okay. But back to a technical question, Wi-Fi 5 gigahertz for compression-less recording, which offers better speed over the AC/AX standards? Not sure if you'll know that.
No, I don't know is the answer to that, because that's all done by GStreamer. So GStreamer is very good at sorting all that out, and I'm not sure that it's the limiting factor. As I said, it's putting the bits and bytes together in the packets, and how you deal with drop packets is the difficult part of it.
Okay, back to the optics. Is the sensor diffraction limited, or is the quality of the lens?
Yes, is the answer to that. The limit is a complicated calculation between the lens, the sensor, and the Wi-Fi. So what Richard's done is he's optimized all of those to work together, which is why the 5 megapixel sensor we think is just right. The lens, if we were to, if the genie were to pop out of the lamp, it would be a better lens that we'd wish for. But we've had quotes of £750,000 to develop a lens, and for the quantities that we're doing at the moment, that's not something we're considering. But we'd love to do it one day. Absolutely love to do that. Okay. Not a better lens. Sorry, it's a microscope lens as opposed to a telescope lens.
Yes, yes. And a sustainability question: is it maintainable, or is this a throwaway item? In other words, can you go to a repair cafe and get it repaired?
No, it's maintainable, absolutely. The fact is, it doesn't need much maintenance. What we recommend is that you just wipe it down with a lab wipe, or I just use a tissue and some gin, and you just wipe it clean. The thing you must remember, that microscopists love to clean lenses. So the first thing they'll do is get a lens wipe on this lens. Now this is a plastic lens, so you mustn't do that because it scratches. It will scratch. We've done tests. It will scratch every time you clean it. So when you clean it, you should just use, I've got a wipe here. These are antiseptic wipes for COVID, which is another question. So what you do is you just use the corner of the wipe like this, and you just flick across the lens. When you scratch the lens, and I say when, not if, it doesn't matter because it's not in the focal plane of the lens, so it doesn't affect the image until the lens is badly scratched. And at that point, any of our distributors can take the lens out and replace it with a new lens. That's not a hard thing to do. We've only ever lost one of these, which was returned from an equine vet, and she dropped it in a bucket of what she said was water, but it wasn't, because it corroded the terminals quite badly. So it was something quite acidic, maybe urea. So that microscope, we replaced the boards, but they were a goner. So so we replaced that. So it's very sustainable. Yeah.
Okay. We've now come back at the end of the questions. Got several comments saying, got to go, brilliant presentation, good luck. And other people have written in on the chat sort of saying brilliant, and they sort of really liked it very much. Thank you very much indeed, Andrew. I'll hand you back to Phil.
Yes, thank you, Andrew. That was a really interesting journey through some of the history of microscopy and your product development journey with ioLight. Really interesting to see how a very mature product can benefit from some fresh ideas and some targeted innovation. And great that it's been done in the UK. So thank you very much. I hope everybody else enjoyed it tonight. Thank you for your time. Please keep your eyes open for our future events. You can find those by looking or searching for the IET Cambridge Network. And remember, please book a place in advance if you want to be sure of a place. So that concludes tonight's event. I'd like to say on behalf of the IET Cambridge Network, thank you for joining us. And you can now disconnect from this Zoom meeting. Thank you.
Thank you for having me.
Pleasure.